Hi, welcome to Surely Physics episode on simple harmonic motion. Simple as in, not much is happening that's beyond that motion. Harmonic referring to a repeating kind of a motion. Sort of like when music harmonizes, you get that continuous, good sounding reverberation that is just continues on for a long time. You could just listen to that stuff forever. So here's an example of simple harmonic motion. There's a mass hanging on the end of a spring. That mass just continuously moving up and down. Doesn't seem like it's changing very much at all. So that's an example of simple harmonic motion. Made a very consistent repeating pattern. Nothing too complicated with it. Here's that same pattern, but I'm going to mark the points in space up and down once it gets started. You can see that those points just kind of move back and forth over one another. The size of the motion is very consistent. It's about the same. So what we have here is SHM, simple harmonic motion. I'm going to put up a piece here on, this is the video that I took, and back it up a little bit. As I move the mouse across the screen here, you see across the red wave pattern, it's going to move the video to match those data points. The data points start right up at the top of the motion right there. And as you notice, this red curve, you call it repetitive curve, a red wave, it makes a very cosine-like function. Now the top does seem to be a little inconsistent. This is a real world application here. There's some vibrations and other things that are affecting its center position. But all in all, if we get rid of that kind of little deviation there, we have a very harmonic motion where that motion continues in a very consistent kind of a way. It repeats itself over and over again. You can see the spacing between the crests of this wave are very consistent as we go across from left to right there. And let me just please take a note that even though the mass is moving up and down kind of over its own path, this does make over time a cosine function. Cosine because I started the data at the top. Now if I had started the data at the middle right there, it would be a sine function. But I did select to start at the top. When I released it, I began by pulling the mass downward from its rest position and then releasing it up. And you can see it there. So yeah, actually, if I track the data from the beginning, this might be a negative cosine function. It doesn't really matter if you start as a cosine or a negative cosine or even a sine function. It'll still have this same kind of repeating pattern over time. Can't really track it back to where it started. Therefore, there's sort of a phase angle you'll sometimes see. I'm not going to talk about that too much in this video, but the phase angle is just where it starts. What part of that motion does it start in? If you look at the bottom graph, this is a plot of the velocity. You see, when I let go of when I start the data here and the spring starts moving, it begins moving in a downward direction. So its velocity actually begins downward. The velocities at the bottom are negative, and they increase to about this point. That's about the rest position of the mass. Then the negative velocities continue. The mass continues moving downward, but it slows to rest right about there and begins moving upward. It might be hard to see my little cursor here, but I'm now in the upward part of the motion where the velocities are positive. And you see up to this point where the velocities are positive and the mass is moving upward, it's going to continue moving upward past the rest position, that starting point. If you look at the top graph, the red one, this point corresponds to a y coordinate of 0. And the velocity corresponds to a maximum velocity. So something we're seeing here, a little pattern, is that the maximum velocity of this mass occurs at the very center of its motion. And the minimum velocity of the mass occurs right there at the top of its motion and right here at the bottom of its motion. Meanwhile, it's got a negative maximum when it's passing downward through, I'm going to go the correct direction here, downward through the center, and a positive maximum when it's passing upward through the center. So you might say, if you look at these two graphs, The top one, the motion pattern, is a cosine, a positive cosine function. The bottom one is a negative sine function. If you take a little calculus, you might realize the relationship between those two. And since you've taken a little bit of physics, you also know that the velocity is the derivative of the position function with respect to time. So if the position function is cosine, what should the velocity function be? A negative sine. And also you might note that the spacing between the crests and the top and the bottom graphs is equal. They have the same frequency. So there's a frequency also to this pattern. How frequently do these waves occur? The other thing you look at is what is the time period for one of these wave cycles. In our next episode, I'm going to be presenting some other scenarios that involve pendulums. And pendulums, just swinging objects that they also have a simple harmonic motion to them. Today, I'm going to simplify the scenario we just started with. And simplify meaning I'm going to take the vertical component out of it, the gravitational component, and we're just going to look at a simple, frictionless, horizontal mass, horizontally moving mass on a spring. So if you can imagine a nice purple spring with a purple mass. Okay, excellent. And we have lots of space to work with. Friction is always approximately 0. We have a frictionless surface here. That'll make it a simple harmonic motion. It's not going to be a damped motion. There's wave damping or that type of thing, but we're not going to have damped motion. Damping is sort of like friction for waves and for repetitive motions. So this is still simple harmonic motion, SHM. And what if we take this mass and we pull it away from its rest position? I'm going to pull it out to here. There's a simulated mass. Where would it be if it were pulled out to there? At this point, what would it do if we released it? It would start bouncing back and forth and back and forth. And if we turn that motion onto its side, we would see a cosine function kind of a pattern as it bounced back and forth. Okay, so that's the big idea going on here. What we could say then is its x position, if we call this to the right the positive direction, as a function of time, is some kind of cosine function. Now the distance we pull it to the side, we're going to call A for the amplitude of that wave motion. So if A is 1 meter, then x of t would just be cosine of something. It would be a 1 times cosine of something over here. Now what goes over here next to the cosine? Well, this has to be a repeating pattern, and it's got to relate somehow to, what do you think it's going to relate to with a mass and a spring? If there's a big, large mass on the end of the spring, that mass is going to have a lot of inertia. So it's going to be more difficult. The greater the mass, the greater the difficulty it would be for that spring to accelerate the mass. It has more inertia. Also, if you have a tight spring or a loose spring, that's also going to affect how often or how long it takes this mass to move back and forth. So right in here, we've got to put an omega. Now this is an angular frequency. I'm calling it an angular frequency now because it's an angle in radians. Instead of calling it a velocity, we're not really looking at how quickly the mass is moving back and forth here. That's for something else. There's not really a spinning motion to call it an angular velocity, but it's a frequency measured in radians. And so you might have a feel for that when you've got cosine of time times a frequency. Angular frequency would be normally, I should say, let's go back to the relationship between frequency and angular frequency. Frequency measured in hertz has units of just cycles per second. Okay, so how many repetitions per second, how many times you go around per second, that's frequency, cycles per second. That's what hertz means. But omega, the angular frequency, is 2 pi f. and that 2 pi is radians. And instead of just numbers of cycles, one cycle is how many radians? It's 2 pi radians to go back around to the start again. Say if you start on a circle, it took one full cycle around, that it would rotate through 2 pi radians. So omega is measured in radians per second. Therefore, if we think about omega t in terms of a cosine, what I need to get out of a cosine, what I'm going to apply a cosine function to, is an angle, not a time. So if we take an omega radians per second times a time in seconds, you'd end up with radians. That's why we're going to use omega. X of t equals a cosine omega t. This is our generic function for the displacement of a mass on the end of a spring. It could be a mass on the end of a string that's swinging back and forth, as we're going to look at tomorrow with pendulums, or in the next episode, I should say. It may be tomorrow. And equals cosine omega t. I like to start out with a cosine because generally, in order to get one of these systems to work, you need to pull the mass to a non-equilibrium position. If the mass is there, it's just sitting there in the middle where the spring doesn't have any net force acting on it. It's in its rest position, it's at equilibrium, so it's not going to go anywhere. So normally the motion starts after you pull it to the side, displace it a little bit, and let go. And it's going to start bouncing back and forth. All right, so if that's the form of the displacement function, what would the velocity function look like? And this is what I alluded to in the actual real data example. Well, velocity, instantaneous velocity, is dx dt. So if we do take the derivative of this function, we're going to get out, let's see, a, and this is with respect to time. So derivative of cosine is negative sine. And we'll have to use the chain rule here, so it's going to be negative sine omega t times the derivative of what's on the inside here times omega. And we'll clean that up a little bit. The velocity function would then be a negative a omega sine omega t. Again, I'm going to talk about that omega a little bit more and how it is affected by the spring and the mass on the spring. So we'll look at that in a moment. Clean that up. So here we have the velocity function. Here we have displacement for a simple harmonic oscillator. And finally, what about the acceleration? I haven't talked about that too much yet, but what do you imagine is going to happen here? If we pull the mass to the side and then release it, what will be the acceleration in the beginning? It's going to be due to the spring pulling back. And that acceleration should be at a maximum here. This is where the spring's force would be at a maximum in this scenario. The spring's force should be at a minimum at this rest position in the middle, where, you know, think about Hooke's law. The force of a spring equals kx, where x is I should say delta x. X is the displacement from its rest position. So the displacement of the mass at this point, after it's zooming back here, when it reaches this point again, the spring will be applying zero net force to the mass. That means there's a zero acceleration at that point. However, at that middle point there, the velocity should be at a maximum. So it's not just going to stop in the middle, it's going to continue moving. Objects in motion tend to stay in motion. And after the mass passes through that center point, then the acceleration is going to be back to the right. It's a restoring force. And eventually our mass is going to get to some position over here, and call that negative a, if you will. All right, the amplitude is the distance from that rest position in either direction. So over here it'll be at a position of negative a, and the acceleration will be to the right and at its maximum. Maximum changes at the end. So we should see a maximum acceleration in the beginning, zero acceleration at like pi over 2, and another maximum acceleration at about pi radians. That's what it would turn out to be. Now remember, pi is like 180 degrees. pi over 2 is like 90 degrees. So just think about those degree compared to radian measures. So what is acceleration? Let's go ahead and get this function. Acceleration is the rate of change of velocity, dv dt. And for acceleration, we're going to take the derivative again. This is a couple of constants out here. We got a negative a omega. And the derivative of sine omega t is cosine omega t. But again, we'll have to take that chain rule, take the derivative of what's inside there, so we get another omega out of that. And therefore, our acceleration of a simple harmonic oscillator with respect to time is a negative a omega squared cosine omega t. There they are. Dynamic trio. All right. Does this make sense? Is the acceleration in the opposite direction of the displacement? It should. This is obeying Hooke's law here. F equals negative kx, showing that whatever direction the x is in, is if it's positive, that means the force and also the acceleration are in the negative direction. As the mass moves to the right, the spring is going to be pulling back to the left. It's accelerated, it's going to slow down until it reaches 0. And then as the mass is displaced to the left, in the negative direction, the acceleration is also negative. Right, so here when cosine is 0, we get a positive 1 here, and x is positive. But when cosine is 0, a would be negative. A little moment later, x is still in a positive position. I might have been mentioning the position earlier on. I meant the velocity. The velocity would be negative earlier. I just botched that explanation, so I'm going to move on. So those are just to wrap it up. That's our x, v, and a equations there for simple harmonic motion. And no, you don't need to memorize them. If you do memorize anything, it's just a simple form of displacement. And the other two don't need to be memorized. They're just going to be the first derivative and second derivative of that displacement function with respect to time. There's the amplitude cosine of omega t. So what is going to be the omega here? This is a mass spring system. And with a mass spring system, if we're going to figure out what this omega is about, it's dependent upon m and the strength of the spring k. The only place those really come up are with forces. Let's therefore think of us the moment in time when we stretch this thing out and release it. At the moment we release it, what is going to be the force diagram? What's it going to look like? Well, there's going to be a force of a spring this way. Of course, there's a weight, a normal force. And friction is about 0. So there's no force to the right. Okay? That means the normal force and the weight, since there's no friction, we don't need normal force. The normal force and the weight, they just cancel each other out. So our net force is only due to the spring. That's why we're making it simple harmonic motion, not complicated harmonic motion. All right. And the force of that spring, its magnitude, is kx. Okay? If we take Newton's second law, then we get a kx. That's a kg. X being the position at the particular time equals ma. Okay? And I should make a particular note here. If I'm calling this the positive direction, because that's the direction of positive displacement, this kx force is in the negative direction. All right? So we've got to the left is the negative direction by defining right as positive. All right, so we got a negative kx equals ma. Wonderful. But the problem is this is a little bit of a differential equation. All right, doesn't work out so nice. And that's because A is the second derivative of x. You see, they're both related. We've got a differential equation here. This is a diffeq. And the only way to solve this is with a little bit of knowledge of what that displacement is going to look like. That displacement's going to look like our old friend from the other page, A cosine omega t. All right? So that's what it is. We have a relationship between x and time, position and time. And we also, from this expression, we also have a relationship between x and a, the acceleration. You might recall from the other page, negative a omega squared cosine omega t. And that's the acceleration. So why not try to solve this with respect to time, or get something more out of this, by plugging these in here. All right, this a is the second derivative with respect to time of displacement. So why can't we plug these expressions in and see what happens? We got a negative k x on the one side, but instead of x, I'm going to plug in a cosine omega t. And on the right side, we got an m. And instead of the second derivative of x or an a, we're going to plug in negative a omega squared cosine omega t. Did we just give ourselves a headache? No, we simplified things quite a bit. You see this negative and the negative, they're going to cancel there. Multiply both sides by -1, they cancel. And we got an a that cancels on both sides. And we got a cosine omega t. The big ugly elephant in the room goes away. And what's left here? We got a mass, we got an omega squared, and on this side we've got a k. Wow, that's not a lot of stuff. So there's a k equals m omega squared. Whoa, what's this saying? Look, the omega, the angular frequency, depends on the spring constant and the mass. That's it. And let's see if this makes sense. If the spring constant is high, it's a tight spring, then that means it should be moving back and forth rather quickly. There's a high frequency. Bigger the k, the higher the frequency. And how about the mass? It's divided by mass. If we increase the mass on the end of that thing, it's going to get slower and slower. The inertia is going to increase to that system. So it's going to make it more difficult. The frequency, angular frequency, is going to decrease. So this totally makes sense. It's all dependent on spring constant and the mass. Now sometimes omega isn't something that's given, so I do want to help you remember that there is a relationship between frequency, period, and omega, the angular frequency. Okay. Sometimes I usually write like omega equals 2 pi f. That's usually what's stuck in my head here. But the relationship between frequency and period is there. Here's omega and frequency. So a couple other things we can get from this. We can get the frequency, but we can also find the period. So I'm going to go ahead and solve for the period. And the period's kind of helpful, especially with like timing devices. You could use a mass on a spring as a timer if you can get it bouncing up and down with a period of 1 second. So sometimes a period is a helpful, recognizable measurement to have instead of an angular frequency. That's why we're solving for it here. And now we've got omega over 2 pi. Instead of omega, I'm going to plug in k over m over 2 pi. And now if I bring well, actually I'm going to leave it right there. In order to solve for period, we're going to invert this side and invert the other. We've got a couple of ratios. If one is to t as root k over m is to 2 pi, then t over 1 is to 2 pi over root k over m. It's called the Scholle flip method right there. But we could also simplify that to 2 pi times root m over k. Because this is like a 1 over root k over m. It's the same as root m over k. So we're just going to flip those, take the reciprocal, and there it is. This is a period for a mass on a spring. 2 pi m over k. So what is this saying? It's, the bigger the mass, the longer the time period to move back and forth, and the greater the k value, the tighter the spring, the shorter that time period to move back and forth. Both of those work. This process I showed you, it's pretty simple. This is going to be the same process I showed you for pendulums. Just apply Newton's second law, get a relationship between acceleration and displacement, and we're going to plug in motion for a simple harmonic oscillator, a system with simple harmonic motion. Plug those both in there, and you're left with, after a little bit of algebra, a relationship between omega and the physical quantities that make up the system. What's going to make it move fast? What's going to make it move slow? The last bit. Earlier, I had Logger Pro up. I had the video, and we're comparing velocity to displacement. So when we're at a displacement of 0, when that mass returns to its original position, note that the velocity is greatest. Right now it's at the lowest point way down here. And velocity is also greatest when the mass is at its highest point. So here's the mass at its highest point. I'm sorry, velocity is greatest. Here we go. Right at the midpoint there, and also on the return midpoint. At each of those midpoints, the velocity is greatest. And I'll just kind of move this through. You see that it's moving fastest right there in the middle, and it pauses up at the top and the bottom of its motion. But always in the middle, you've either got a maximum negative velocity or a maximum positive velocity. All right, so are you getting a sense here that conservation of energy should work as well? And it does. It works quite nicely. So that's the last little bit here, talking about energy in this system. Okay, so what if I do have this mass? It's on a spring. This is normally the rest position. I'll call this y equals 0. Got a y instead of an x here. And this mass is going to go from this point down to this point. Okay, it's going to go down to here and then back up. Just going to jiggle kind of in between those two positions. All right. The distance here would be a, the amplitude. Okay. So what if we had a situation where a mass was dropped? And what I'm going to do here is I'm going to go ahead and give some values to this. We're going to have a mass is 1 kilogram, amplitude of a ½ meter. We'll use a K value. And I'll use a K value of 100 newtons per meter. That's the K for the spring. Now let's see, do I need anything else? I think that's about it. All right. What would the velocity function look like? Remember, the velocity is going to be the first derivative of the displacement function. All right, so the velocity should look like this. Should look like negative a omega sine omega t. That's from our first page in this presentation. That's our velocity. Okay, so plugging in what's known here, a is 0.5. Omega is, omega is root k over m. So it's going to be a root 100 over a mass of m. Oh, good, that's easy. Root of 100 is 10. Omega is 10 radians per second. All right, so there's going to be a 10 sine of 10t. That's our velocity function. Clean it up just a little bit. Half of 10 is 5 sine 10t. Okay. So after half that motion, when this moves down to here, what's our maximum V going to look like? Maximum V is when 10t equals pi over 2. All right, that's 90 degrees. All right, sine of 90 is 1. That'll give us our maximum V. So V max is when that quantity 10t would be equal to pi over 2. All right. So if you ever wondered or asked, at what time is this moving through the center? Well, the first time interval it would be moving through the center would be at pi over 20 seconds. We can leave it as that because pi is just this absurd number that doesn't ever come out even. Okay, so it's one thing you can figure out. When is the Vmax going to be? And what is it going to be? What is the Vmax going to be? Well, at sine of 90 degrees is equal to 1. If that's our Vmax, our maximum velocity is going to be -5. Or if we look at that, our Vmax, or maximum speed, is going to be 5 meters per second. Okay, so that's analyzed using the motion. What about using energy? What's the energy form at the top? At the top of this, that spring is it's a bit looser, and they might have a particular stretch length, okay, to start with. There's a couple things that take in consideration here. How far is that spring stretched when it's at the top or when it's at its rest position? We can actually figure out the x when it's at its rest position, right? So when at the rest position we just let a mass hang there on the end of the spring, that means the spring force is equal to the weight at that moment. And this is kind of important to work with here. So just follow me here for a moment. And if that's true, when you take the sum of all the forces equals ma, using a little Newton's second law here, and the spring force minus the weight equals the mass. My mass is 1. But if it's just hanging on the end of the spring, it's at rest. So the acceleration is 0 as well as the velocity. So at this point, we've got the spring force equals the weight. Okay, so how far is that spring stretched? Well, if the spring is 100, I'm going to go ahead and put the kx here. So k delta x is the quantity of that spring force, equals mg. Mass is 1, g is 9.8. Spring constant is 100. So how far is the spring stretched when the mass is hanging on that spring there? That's what we can solve for, that delta x equals 9.8. So that midpoint is when the spring's at 9.8 over 100. We're going to say this is essentially 10, just to make it a little easier here. 10 divided by 100 is 0.1 meters. Okay. I produced a little issue for myself here, but dang it, I guess in reality, surely, I just came up with this on the fly. The amplitude's not going to be 0.5. So let's modify this a little bit. Since the rest position is 0.1 meters, it's not going to be bouncing up into itself. So let's modify this just a little bit. The amplitude I'm going to make 0.05. Amplitude is 0.05. And this will be, instead of 5, it'll be 0.5. Just dividing everything by 10 here. Okay, that's still dealing with the time over there. That's not a problem. So our Vmax, 0.5. There we go. All right, problem solved. Now we're not going to break physics or the universe or anything. Okay. All right, so here's our scenario now. The rest position is when we've got the spring kind of stretched out. It's got a mass hanging on there, and it's now fallen down 0.1 meters. And this mass is going to be bouncing up to 0.05 above that and 0.05 below that. That's our bouncing range. Okay. What kind of energy will the mass have at this point? Well, it's at a position above its lowest point. We call that gravitational potential energy. And at the highest height, is it moving? No. So if we consider kinetic energy, no, it doesn't have any up there. Is the spring stretched out from its rest position? Yes, and that's why it was important to come up with all this kind of stuff. Now at the top there, the spring's rest position without anything hanging on it is kind of up here. Okay, we've stretched it down by hanging the mass on it. Now it's only bounced up 0.05 meters, about 5 centimeters. Okay, so it's up at this far. This is the rest position, and down here is the midpoint of the motion. This is the spring's rest position, not the system. When the system comes to rest, the mass is hanging right there in the middle. Should make that defined there. All right, so at the top of its motion right here, there's gravitational potential energy and elastic potential energy. It's pulled out it's pulled out 5 centimeters from its rest position. Now, what about the middle? Getting back to this, if we want to know the velocity at the middle here, what is the velocity? Well, at this point, it's moving. It's got kinetic energy. It's not stopped at the top. Is it still a potential energy above the lowest point in the system? Yeah, I'd say there's some potential energy left there, gravitational potential energy. And is the spring stretched out from its own rest position up here? Yeah, there's going to be some elastic potential energy down there. Now, if we consider the energy at the top to the energy in the middle of that motion, this is just another way to solve a scenario like this. What is the velocity in the middle? I hope I get that on video. Little old person burp. The energy at the top is composed of gravitational potential energy and elastic potential energy. And I'll put a little O there for the initial. And down here at the bottom, at this next, or at the middle point, there's kinetic energy, call it final, plus gravitational potential energy final, plus elastic potential energy final. If I'm wrong about any of these being here, then I'm going to go to 0 value when I start to think about it and plug some numbers in. Let's substitute UG. UG is MGH. UE is half K delta X squared. And this is more of a delta Y here, but I'll just keep it X for the spring. Let's not mess it up. And that's the initial displacement of the spring. Then we'll have a 1/2 mv squared. This will be the final velocity that we're looking for. And again, we got a gravitational potential energy, height final, and a elastic potential energy, delta X squared final. Plug in what we know. We're going to need the mass, 1. G is, I'm going to use 10 again. And the height. All right, the initial height above the lowest point, if we call this the height, then that distance is 0.1 meters. Height above the lowest point. Hope I wasn't too fast on that. There's a lot of different distances. There's the height, there's the displacement of the spring. The delta X is always from where the spring would be at rest and not have anything hanging from it. Okay, so, but this height, I'm calling a height of 0 down here, so therefore the highest point above that would be 0.1 meters, 0.05 plus 0.05. Spring constant is 100. And up here, the displacement from the rest position of the spring is only 0.05. 1/2 mass times final velocity squared. And down here in the middle, that's where we're at now. Going to have a mass of 1, g of 10, and a height at the middle point is 0.05. Then instead of running this into the edge of my screen, I'm going to move it over. We've got a 1/2 spring constant. And now what's its displacement at the middle here? Well, we've got 0.05 plus another 0.05. So the spring's displacement is 0.1 squared. Take a look at what we got here. We've got something that's completely solvable for VF. 10 times 1/10 is 1. We got a 0.00, oh my goodness. It's going to be a 25, 1, 2, 3, 4, 0.0025 times 50. Half of 100 is 50. Equals, got a 1/2 VF squared. And 10 times 5/100ths is a half. There's another 50 times 0.1 squared is 0.01. Do some more math. Got 1 plus 50 times 0.0025. You get that right? 50 times 0.0025, 0.125. Just a little bit of algebra here. We got plus a half. And 50 times 0.01 is still another a half there. Oh, look at this. Half plus a half is 1. Subtract 1 from both sides. Those two cancel. We're down to 0.125 equals half VF squared. Well, I'm getting a feeling about this. Multiply both sides by 2. 0.25 equals VF squared. And if we take the square root of both sides, guess what the result is? A half meter per second. Using energy, conservation of energy, and look at that, our Vmax. Using the motion of a simple harmonic oscillator, arrive at the same place, our maximum velocity. You can get that through writing out the equation. You can get it through conservation of energy. Sometimes you're not given enough information to work out the omega, to work out the rest of the stuff, but you can approach these problems from either way. And from this presentation, I hope you get that couple key points here. First, just from the displacement of a simple harmonic oscillator, it has an amplitude, a maximum distance it covers. And it's an oscillating motion, so it's either governed by the cosine function or the sine function. And once you have the displacement, use your old derivatives to find the velocity and acceleration. Now that you have your calculus skills under your belt. Occasionally you need to determine what an angular frequency is, and that's how quickly the system is going to oscillate back and forth. And it's all dependent on the physical makeup of the system. So in the next episode, we'll be looking at pendulums and their physical makeup, but everything will have the same displacement functions and velocity and so on, just a different kind of omega. You get that omega by applying a simple Newton's second law application. One thing you'll find all in common is that displacement side will have a negative attached to it. There's a restoring force to this, and that's what keeps the oscillating motion going. It always has to be that restoring force. For a pendulum, the restoring force is the direction of gravity. So gravity depends on or affects that restoring force. But you always get this differential equation here, an x related to its second derivative. And that's where our expressions for displacement and acceleration come in. Plugging those in help us to find the omega value. And just gave you an application, another look at it in our last step here. This is not always necessary, but it's another view, another look, that we can find quantities like velocity and maximum displacements by either using the X, V, and A functions, or with an application of conservation of energy. This one makes it look a lot, more busy using conservation of energy, but I think what my eye picks up on is there's a fish here, okay? There's a fish. And it's a happy fish. That's the end of this episode.